Alright guys, October 26th through the 29th, Algebra 2. Make sure you have your packet out in front of you. Guys, this lesson is full of information, a lot of stuff that won't be in your packet. So please make sure you're writing down notes as we're going. It's just, there's a lot in here. Don't forget, if it does ask you to graph something, if you do not have a graphing calculator at home, you can use the website, desmos.com. That will allow you, it works very similar to the graphing calculators we have in class. So you can use that to help you graph something. You are going to see some things that say graph. And I realize that we don't have graphing calculators, but you can go to this website. It's free, and it will graph them for you. Alright, so it says sketch the graph of f of x is equal to x squared. Alright, so normally what we would do is we would spend a lot of time talking about how to graph this. I'm not going to spend a lot of time on how to graph this. Guys, if you want to graph something, if you don't have a graphing tool in front of you, you can plug a number in for x and that will give you your y coordinate. So if I plug 0 in for x, 0 times 0 is 0. So I know that it would be here. Alright, and then I could plot points and then I could actually graph it. To save us just a little bit of time, what we want to do is I want to show you what x squared looks like. This is what the graph of x squared would look like. So sketch that on your paper. It's not going to be perfect because I'm not taking the time to do all the scales and everything. We're mainly looking at what we know about this. So let's talk about the graph of f of x is equal to x squared. Alright, what do you notice about this graph? You should notice that it never goes below the x-axis. If we were to actually draw this appropriately, you would see that it's equal on both sides of the y-axis. Alright, so in other words, I could probably fold it in half and it should match up. Alright, so let's talk about why it never goes below the x-axis. Why will it never go below the x-axis? Think about this when you square something. Even if I put a negative number in, a negative number times a negative number is going to give me a positive number. So when I square something, I'm always going to get a positive number, which is why my graph never goes below the x-axis. My x-intercept would be 0, 0. I could trace that on my graphing calculator and see that. Alright, so now it says, what will the graph of g of x is equal to x to the 4th look like? Alright, so this is my f of x is x squared. So it wants to know what the graph of g of x is equal to x to the 4th. G of x is equal to the x to the 4th is actually the same thing as saying g of x is equal to x squared, and then I'm going to quantity square that. Well, I kind of already know what x squared looks like, so we could probably say that it's going to have the basic same shape. Alright, but we need to look at something else. So, if I were to put the number 2 in here, 2 times 2 is 4, times 2 is 8, times 2 is 16. What you're going to see with the graph of g of h is equal to x to the 4th is this. know it's kind of hard to see, but the graph of x to the fourth is this graph here. Notice that it increases quicker than f of x does. All right, so it's going to have the same shape. It's just going to increase quicker than f of x does. All right. Both graphs still pass through 0, 0. Basic same shapes. Near the origin of the graph of G is flatter than the graph of F. So it does get a little flatter here than f of x. All right, so the last thing it says, what do you think the graph of h of x is equal to x to the sixth looks like? Well, look at this. That is the same thing as saying x squared times x squared times x squared. So now I'm taking my original graph and I'm multiplying that original graph 3 times. All right? So it's still going to pass through the same origin. All right? Since we're squaring and multiplying by squares, the graph of h should look about the same as the graphs of f and g. But what do you think it's going to do? You think it's going to increase faster or slower? It is going to increase faster, but be even flatter near the origin. So it's going to look like this. All right, so that third graph, h of x is equal to x to the sixth. All right, it's going to increase quicker, but it's going to allow you a flatter base. All right, so really quickly, let me kind of show you this. This might help you to see it a little bit better. All right, notice that the higher my exponent gets, the flatter the base is. But it still doesn't go below the x-axis. And I'm still looking at an x-intercept of 0, 0. All right, so let's use these graphs to talk about something called end behavior. All right. I want you to compare and describe the behavior of the value of f of x as the absolute value of x increases without bound. All right. We have a term called end behavior. That is a way to talk about a function and what happens to its graph beyond the bounded region of the coordinate plane that is drawn on paper. All right? Because basically what I'm wanting to know is what's going to happen to this graph outside of this window that I have on my graphing calculator. Or what's going to happen to my graph, excuse me, I had to sneeze. What's going to happen to my graph once I run out of paper to draw it on? Excuse me. That is the end behavior that we're talking about. How's my graph going to end? What's it going to look like? Is it going to end? Excuse me. Goodness. All right. The end behavior is a way to describe what happens to the function as x approaches positive and negative infinity without having to draw the graph. All right? Because eventually we're going to run out of paper. Like I said, I can make my window only so big or so small on my graphing utility. So what's going to happen? All right, so we have a phrase, and I have to be really careful about how I introduce this to you because I don't want you to be confused. But we have a phrase that looks like this. The phrase is said to read like this. As x approaches positive infinity. Or I could say as x approaches negative infinity. So in other words, what's happening as my graph is reaching positive infinity? If I'm looking at these graphs, I want to know, I'm going to keep drawing and keep drawing and keep drawing. And I can keep going and going and going and going and going, which is where I get that positive infinity. This is where I get that negative infinity. So what is happening? This is the end behavior. It is not that x is actually moving along the number line. It's just what is happening to our graph. All right, so in behavior, you have a function, okay? We've got the function of f of x, the function of g of x, and then h of x. So we want to know what happens to the values of the function as x approaches positive infinity and as x approaches negative infinity. All right, so let's look at this for just a moment. You do not have this in your packet, so it's really important for you to look at this. Okay, so look at this graph. All right, this graph looks a little different than the ones that we did in the opening exercise. Okay? So I want to look at this, and I want to make a generalization about the end behavior of the polynomials. All right? This is the graph of y is equal to f of x. All right? So I want to know, so I'm looking at this, and my graph is going this way. So I want to know, as here's my positive infinity. How do I know this is positive infinity? Because I'm in quadrant 1. My graph is ending in quadrant 1 on this side. So I'm approaching all positive numbers. So I want to know what is happening as x approaches positive infinity. As I'm going this way, as my x gets bigger in positive numbers, what is happening to my graph? My graph here is approaching positive infinity also. Okay? Never, as I'm going, will my graph drop back down like that. It is going to continue going up, up, up until you run out of whatever, numbers, whatever. That's never going to happen. All right? Let's look at this part here. Look at what happens here. I'm going into negative numbers here. So this is as x approaches negative infinity, because I can continue drawing my number line out. What's happening to my graph here? F of x is approaching negative infinity. Okay? So we can conclude that as x approaches negative infinity, my function is going to approach negative infinity. In other words, my end behavior is going to be negative infinity. As x approaches positive infinity, with this particular graph, my function will approach positive infinity. All right? All right. So here's what I need you to do. We need to find some place to write a little thing here. These are what we call even degree functions. All right? So you need to get a separate sheet of paper, whatever you need to do. We are looking at even degree functions. Remember, I can look at my degree of a function by looking at the highest exponent. So if it's x squared, x to the 4th, x to the 6th, x to the 8th, then these are even degrees, okay? Looking at the functions that we graphed at the beginning, x squared, x to the 4th, x to the 6th, I see that as x is approaching positive infinity, what's happening to my end behavior? My graph is going to keep going up. So as x approaches positive infinity, my function f of x approaches positive infinity. Looking at this, let's look at what happens as x is approaching my negative numbers. As x approaches negative infinity, what's happening? I'm still getting a positive number. So as x approaches negative infinity, my function still is approaching positive infinity. Now, there's another little thing here that we need to look at. These would be examples of f of x is equal to x squared. F of x is equal to x to the 4th. Alright? I want to show you something else. Let's do 4x squared. Alright, look at 4x squared. It's a positive, it's an even degree function, so therefore it is still approaching positive infinity on the positive side. It's still approaching positive infinity on the negative side. But what happens when I have this? Let's do negative 3x squared. Look at my degree. I have an even degree function, but look at my graph. It's now on the bottom. So, this right here only goes if the leading coefficient is positive. So, f of x is equal to 2x squared. F of x is equal to 10x to the 6th. As long as that leading coefficient, that number at the beginning, is positive, this is what I'm going to know about my graph. Let's look at what happens if my leading coefficient is negative. As x approaches positive infinity, what's happening to my numbers? As x approaches positive infinity, f of x, or my function, is approaching negative infinity. Alright? As x approaches negative infinity, look at what's happening. My function is approaching negative infinity. Okay, so this is if the leading coefficient is negative. Alright, so an example might be f of x is equal to negative 3x squared. Now remember, these are still, I'm still dealing with even degreed functions. Okay? I'm still dealing with even degree functions. Or if I have f of x is equal to negative x to the 4th. this is what would be happening. All right. So it says sketch the graph of f of x is equal to x cubed. Now notice I'm not looking at an even degree function now. All right, so let's sketch the graph of x cubed. Oh, look what happens here. Look at that graph. All right, so let's sketch that graph. So it looks like this. All right, so this is f of x is equal to x cubed. All right. What will the graph of f of x, or g of x is equal to x to the fifth look like? Well, let's look at x to the fifth. Look at this one. Let me change my window just a little bit so we can actually not cram them together. We'll go, yeah, that helps a little bit. So notice what happens. It kind of does this. Sketch on the same coordinate plane. What will the graph of h of x is equal to x to the seventh? Well, let's look at what x to the seventh looks like. It's kind of hard to see, but it is flatter. It's more like this. All right. So look at the difference between my graphs. These are even functions, even degree functions. These are odd degree functions. All right? So let's look at this and let's see what happens here. Let's look at our, let's do some general rules here for our odd degree functions. All right. Let's look at our odd degree functions for a moment. Once again, x to the third, x to the fifth. We're probably going to be looking at positive leading coefficients. So in this case, all of ours had ones, so therefore they were all positive leading coefficients. Let's look at what happens. As x approaches positive infinity, what's happening here? My function is approaching. All right. As x approaches my negative numbers over here, my function is it's going into the negative numbers. All right, and that's if our leading coefficient is positive. So an example might be f of x is equal to x cubed. Or f of x is equal to 2x to the fifth. Okay? It's an odd degree. My leading coefficient is positive. All right, let's look and see what happens if we change that leading coefficient to a negative number. Maybe it will stay the same. Let's see. So we'll do negative x cubed. Look at what happens. My graph actually flipped. All right. As x approaches negative numbers, what's happening to my function? It's actually going to the positive So as x approaches negative infinity, my function approaches positive infinity. All right? Look at this. As my x values become positive numbers, my graph is going into the negatives. So as x approaches positive infinity, my function is going to the negative. That is if my leading coefficient is negative. Okay? So this could be f of x is equal to negative x cubed. Alright? I told you guys there's a lot of stuff here. A lot of stuff here. Alright. Consider the following function. F of x is equal to 2x to the fourth plus x cubed minus x squared plus 5x plus 3 with a mixture of odd and even degree terms. Predict whether its end behavior will be like the function in the opening exercise or more like the functions from example 1. Graph the function f of using a graphing utility to check your predictions. Alright, so we would look at this and say, okay, well we've got a leading coefficient of 2 and it's positive and it is a positive degree, or it's an even degreed function because the highest degree is 4. So I would suspect that it would be more like our first graphs. Alright, if you remember, our first graphs looked like this. They were like this. This was our positive. This was our negative degree function. Or we had functions that looked like this. Our even degree or our odd degree functions look like this. Alright? So they want to know, what do we think? Well, I would suspect, based on the numbers, that it would look like, it should look more like even degree functions. Because the degree is 4. Okay? But I've got some odd things thrown in there, I've got even things thrown in there, so I don't know what it's going to look like. Alright, so let's look and see what it looks like. When we graph it, we have 2x to the fourth plus x cubed minus x squared plus 5x plus 3. When we graph it, it doesn't exactly look like our even degree function, but it behaves very similar to our even degree functions. Even though it drops below the x-axis, notice I'm not going up and down. I have that U shape. So it behaves more like an even function. Okay? Consider the following function. F of x is equal to 2x to the fifth minus x to the fourth minus 2x cubed plus 4x squared plus x plus 3 with a mixture of odd and even. Predict whether you think what it's going to look like. Okay? So I'm looking at this. It's a positive leading coefficient, but my highest degree is a 5. So therefore, it should look more like odd degree functions. Alright? But we have to see. So I have 2x to the 5th minus x to the 4th minus 2x cubed plus 4x squared plus x plus 3. And look, it doesn't look exactly like our odd degree functions, but the behavior of it has that kind of S-looking type curve. So this one does behave more like an odd degree function. Thinking back to our discussion of x-intercepts of graphs of polynomial functions from the previous lesson, sketch a graph of an even degree polynomial function that has no x-intercepts. Basically what you would do is add something to it. You could do f of x is equal to x squared plus 1. Alright? And if you draw that, because it has that plus 1, whoops. Let me go back up for just a second. Messed that up. Because I have that plus 1, because I'm adding that 1, then therefore it does not have an x-intercept. It would look like this. Similarly, can you sketch a graph of an odd degree polynomial function with no x-intercepts? Alright? This one probably will take you a few minutes to figure out, but what you're going to figure out is you cannot do that. There's always going to be a cut-through nature, because if you look at our odd degree functions, it's always going to cut through somewhere. There's always going to be an x-intercept somewhere, whether it be at 0 or -1 or whatever. Okay, there's always going to be a cut through. So there always will be an, which will give you an x-intercept. Okay, always. Okay, so here's what you need to understand. Odd degree polynomial functions are always going to have at least one x-intercept. Alright? So there's always going to be at least one 0. The graphs of even degree polynomial functions may or may not have x-intercepts. Alright. Last part of our lesson. The Center for Transportation Analysis studies all aspects of transportation in the United States, from energy and environmental concerns to safety and security challenges. A 1997 study compiled the following data of the fuel economy in miles per gallon of a car or light truck at various speeds measured in miles per hour. The data is compiled in the table below. Plot the data points using a graphing utility. Which variable is the independent variable? Alright. huge amount of time, but what you're going to see is it would look something like this. All right, if I were to plot these points, it would look something like this. So it wants to know which is the variable is the independent variable. In other words, which one can act on its own. Speed is the independent variable. The speed has absolutely nothing to do with the fuel economy. All right? This data can be modeled by a polynomial function. Determine if the function that models the data would have an even or an odd integer. Well, if I'm looking at it, it seems to have what kind of shape? It seems to have that U shape, which means it appears to look like it's going to have an even degree. All right, so it appears that it's going to have an even degree. Is the leading coefficient of the polynomial that can be used to model this data positive or negative? Well, look at this. Going back here, if it were a positive, the U would go up. If it's negative, the U would go down. So look at the shape of my U. It looks like it's going to be negative. Due to the shape of the graph. List two possible reasons the data might have the shape that it does. Alright, so why? Well, if you know anything about cars, you know fuel economy improves at a certain speed. Alright, but then wind resistance at higher speeds makes it become worse. You know, things like that. Wind can be a factor, depending on where they're measuring, if it's a windy place. Alright, guys, vocabulary. Make sure you're looking at the vocabulary. If you did not write this down, I guarantee you're going to want to write this down because it's going to become something that you will need to keep. So pause the video, write it down, whatever you need to do. Alright? Once again, guys, if you need to graph something, you can use Desmos.com. If you need anything, reach out to me. Guys, I don't know, just email me because I don't know how much I'm going to be available because I'm not sure what our work schedule is going to be like next week. So just let me know if you need anything.